Hello everyone, this is Dr. C.H. Srinivasarao, working as professor in the Department of Electronics and Communication Engineering, Vardhaman College of Engineering. In this video lecture, I am going to discuss a topic called multi-stage amplifiers in the subject electronic circuit analysis. As I said, the topic for today's class is multi-stage amplifiers. So, the moment we heard about the name multi-stage amplifiers, immediately three basic questions will arise. The three basic questions are: what is a multi-stage amplifier? Then number two, why we need a multi-stage amplifier? Then finally, how to design a multi-stage amplifier? These are the three basic questions will arise the moment we hear the name multi-stage amplifiers. First of all, to get the answer for a simple question, what is multi-stage amplifiers? Just look at this block diagram. A multi-stage amplifier is made up of n number of individual single stage amplifiers, or more technically speaking, if two or more number of single stage amplifiers are cascaded or connected in series, a multi-stage amplifier will result. That is what this block diagram is telling us. Of course, when you are coupling or cascading different stages of amplifiers, we are going to use a coupling element, maybe a capacitor or an inductor or a transformer and so on. That is okay, we will talk about it at later stage. So, by means of a coupling device, if you cascade or interconnect various stages of amplifiers, two or more number of stages of amplifiers, the resultant amplifier becomes a multi-stage amplifier. Now, the basic question that arises for us is why we need a multi-stage amplifier when already we have single stage amplifiers available. So, for this the simple answer is basically single stage amplifiers are low gain amplifiers. They can amplify signals right from millivolts and above. That means to amplify signals in the range of millivolts and above, we design single stage amplifiers, where single stage amplifiers are basically low gain amplifiers. But unfortunately, when the signals are arriving from natural sources, the signals are very weak in amplitude, they may be in the range of microvolts. For those signals to be amplified, single stage amplifiers are not suited. Under these circumstances, when we design a multi-stage amplifier concept is the overall gain of the multi-stage amplifier will be the overall gain in a multi-stage amplifier AV equal to, or simply A equal to, A1 means gain of the first stage into A2 gain of the second stage and so on into gain of the nth stage. So, that means this simple formula is telling us in multi-stage amplifiers overall gain is the product of gains of individual stages. As a result, one can easily understand that in multi-stage amplifiers gain is going to be very high. So, basically multi-stage amplifiers are very high gain amplifiers. The question here is, the high gain in multi-stage amplifier, can it reflect on high output voltage or high output? No is the answer. High gain will not reflect on high output. High gain is meant for amplifying very weak signals, means input signals in the range of microvolts can be amplified up to certain range of volts or certain over a range of volts. That is what multi-stage amplifier is meant for. Then finally, how to design a multi-stage amplifier? Roughly we can conclude with this block diagram. A multi-stage amplifier can be implemented or constructed by cascading or connecting n number of individual single stage amplifiers in series. This is just a generalized statement, But if you want to know more about how to design a multi-stage amplifier, we have to go for the analysis of individual multi-stage amplifiers. We have to look into the design of the multi-stage amplifiers, which we will consider in the second video lecture. But in this video lecture, I am going to restrict my discussion to this coupling device. If you look at this block diagram carefully, block diagram of a multi-stage amplifier carefully, in order to construct a multi-stage amplifier, I said two or more number of individual stages are cascaded or connected in series by means of a coupling device. By means of a coupling device, they are interconnected. The coupling device can be a normal connecting wire, as simple as a connecting wire, or maybe a capacitor, or maybe an inductor, or maybe a transformer. So depends upon the type of coupling element used in between different stages of amplifiers. Basically, coupling schemes, there are 4 coupling schemes proposed by the designers. So I am going to discuss about the merits and demerits of various coupling schemes used in multi-stage amplifiers in this lecture. As I said, there are 4 different coupling schemes used in amplifier circuits. With respect to all those 4 coupling schemes, what will be the benefits we will have and what will be the drawbacks we are going to face because of those coupling schemes when we implement them. This is the topic for today's class. Then look into the coupling schemes we have. There are 4 coupling schemes generally implemented in amplifier circuits while cascading them. One is direct coupling, second one is RC or capacitive coupling, third one is transformer coupling, and the fourth one is tuned circuit or inductive coupling. These are the 4 coupling schemes we will have. Now I will consider one by one merits and demerits of each coupling scheme one by one. First, let us start with direct coupling. Now if you look at this diagram carefully, the input signal is directly given or connected to the base of first stage, means without any additional coupling element like capacitor or inductor or transformer. Just by means of a connecting wire, the input signal is directly applied to the first stage. Then the output of first stage is again directly connected to the input of second stage. Then and so on, the output of last stage is directly connected to the input load resistance. As a result, this kind of coupling scheme is popularly called as direct coupling, because input signal is directly coupled to the first stage, output of first stage is directly coupled to the second stage, output of second stage is directly coupled to the load. This kind of coupling scheme is popularly called as direct coupling scheme. Now let us consider the advantages of this coupling scheme one by one. The fundamental advantage of this coupling scheme is because the input signal is directly connected to the base of first stage or to the input section of the first stage, given a chance, we can apply any AC signal or DC signals also. That means whenever you need AC signal amplification, that is the primary duty of this amplifier, which can easily be done. On the other hand, in case if you want any DC signals to be amplified, you can apply the DC signal to the amplifier directly, because there is no capacitor or reactive element connected here. DC signals cannot be blocked by this direct coupling scheme. Therefore, DC signals can be given as input to the first stage, so that amplification is possible against DC signals also, which is not possible in RC coupled amplifiers. If you go for capacitor coupled amplifiers, if you place a capacitor in between input signal and amplifier, the capacitor will block the DC signals, will see that only AC signals are applied. Therefore, DC signal amplification is not possible in case of capacitor coupled amplifiers, which is possible in case of direct coupled amplifiers. This is the basic advantage of this coupling scheme. Then the second advantage is, if you look into the frequency response of this coupling scheme, you can easily understand that there is a large bandwidth in this case. Look at this. Just now I said DC signals also can be amplified. What is the frequency of DC signal? 0. That means right from f equal to 0, signals gets amplified up to some high frequencies. Up to some high frequencies, signals gets amplified. That means if you look at the bandwidth of direct coupling scheme based amplifiers, the bandwidth will be considerably large. That is what the second advantage is. The amplifiers which are implemented using direct coupling scheme can have large bandwidth. That is the second advantage. And the third advantage is, of course, understandable. Just by looking at the circuit itself, one can easily come to this conclusion. No additional coupling element is required. Hence, the cost of the implementation cost of the circuit is very less. This is the third advantage of the circuit. However, this direct coupling scheme suffers so many drawbacks. Let us consider them one by one. Yeah, the basic disadvantage of this circuit or the serious drawback of this circuit is improper isolation of DC conditions. Improper isolation of DC conditions among individual amplifiers is the basic serious drawback in the circuit. Let us see what is that. What does it mean? What is the improper isolation of DC conditions? In case if improper isolation of DC conditions takes place, what could be the end result? Let me try to explain that. Look at this. We know for every single stage amplifier, while designing every single stage amplifier, we maintain operating point, means we will maintain certain DC conditions. With the help of the DC power supply, we will maintain certain amount of DC base current IB or IBQ for stage 1, so that ICQ is maintained at the operating point, desired location of operating point. Similarly, for the second stage also the same story. We will maintain certain amount of base current, DC base current, depends upon the specifications of the BJT, and we will maintain certain amount of collector current which is at the operating point, which is meant for the operating point to be located. Under these circumstances, if you do not have any isolation between the individual stages here, if you do not have any separation between the two stages here, there is a problem, serious problem of the DC current of DC collector current of first stage may be directly connected to the base of second stage, which may interfere with the base current of the second stage. That means the DC current, base current of second stage and collector current of first stage may be mixing. As a result of that, the operating point or operating point location of the second stage may be completely shifted. For the second stage, operating point is completely shifted. Similarly, look into the first stage also. When the input signal is directly coupled to the first stage, the unwanted DC component that is arriving from the natural source signal may be directly added to the existing base current, which will automatically shift the operating point of the first stage also. As a result, the total amplifier's operating point is completely unstable. That's what the problem here. Operating point of the amplifier becomes unstable and leads to unfaithful amplification. This is the serious problem in direct coupled amplifiers. The next one is, of course, when the input signal is arriving from natural sources, it is expected that the input signal is not only need not be 100% AC, it may have certain amount of unwanted DC component or noise content also. When there is no prevention or precaution taken at the input side to block or to stop that noise content, there is a possibility that that noise content may directly enter into the amplifier and may get amplified, and as a result of that, at the output section of the multi-stage amplifier, that noise content gets highly amplified and delivered into the load, which is completely undesirable. That is, noise signals amplification during AC signal amplification is the other drawback in the circuit. Then finally, of course, improper impedance matching. We know there is no flexibility for us to adjust the output resistance of the last stage, which is going to interact with the load. You cannot maintain the impedance matching situation in this amplifier circuit. As a result, impedance matching, improper impedance matching is the end result. The second coupling scheme is RC coupling or capacitive coupling. If you look at this diagram carefully, the input signal is coupled to the first stage via a capacitor C. The output of first stage is coupled to the second stage via this capacitor. The output of second stage is coupled to the load via this capacitor. So altogether, this is a capacitive coupling scheme. You can easily notice that. Now here also let us try to discuss the merits and demerits of this scheme. First of all, if you look at the first advantage of this circuit, excellent isolation of DC conditions of individual amplifiers. Yeah, exactly the same one as I have mentioned that as a drawback in the previous case. That means because of the direct coupling scheme, there is a mixing of DC conditions from stage 1 to stage 2, stage 2 to stage 3 and so on, that leads to improper isolation of DC conditions, and that leads to operating point instability in case of direct coupled amplifiers. Exactly that problem is targeted in this coupling scheme. See, when we have a capacitor in between the first stage and the input signal, the DC components arriving from input signal automatically blocked, because basically capacitor will act like open circuit for DC signals. Therefore, this capacitor will simply block the DC components coming from input signal to the first stage. As a result, whatever the DC base current you maintain for operating point purpose remains as it is, there won't be any change in that current. As a result of that, the collector current in the first stage remains as it is, as you have at the collector current which you have maintained. Then the output of first stage, when it is coupled to the second stage via a capacitor, this capacitor is capable of creating isolation between first stage and second stage. As a result of that, the DC currents are properly isolated. There won't be any mixing of DC currents of stage 1 and stage 2, stage 2 and stage 1 and so on. As a result, excellent isolation of DC conditions among individual stages. If there is an isolation of proper isolation of DC conditions among individual stages, automatically what happens? The second advantage, extended advantage, is operating point of individual stage will be stable. If operating point of individual stage is stable, what is the advantage? Automatically faithful amplification is guaranteed. That is the advantage of this circuit. Then the next advantage of this circuit is, if you look at the frequency response of this RC coupled amplifiers, you can understand the third advantage here. Just look into the frequency response of this amplifier, RC coupled amplifiers. Due to the presence of coupling capacitors, lower cutoff frequency is established, and due to the presence of junction capacitors in BJT, upper cutoff frequency will be there. As a result, the amplifier will have a finite amount of bandwidth between FL and FH. As a result, signals in a specific range of frequencies only can be amplified, that too of our choice. Why? Because FL is in our control, because the coupling capacitors are designed and connected by us only. As a result, this FL value is established by us only, and this FH, the upper cutoff frequency from the transistor, from the internal capacitors of the transistor, we will set this upper cutoff frequency. As a result, both FL and FH are in our control. As a result, the bandwidth of the amplifier is in our control. That means we can amplify the signals of our own interest only. We can instruct the amplifier to amplify signals of our own interest. So, as FL and FH are in our hands only, we can instruct the amplifier to amplify signals of our interest only. That means signals in a specific range of frequencies can be amplified by the circuit, therefore only desired signals can be amplified. That is the next advantage. Then, since capacitor is used as coupling element, DC signals or noise is blocked. Understandable? In the previous case again, when we talk about the drawback of direct coupling scheme, I said one of the drawback of direct coupling scheme, I said because of the absence of reactive elements, the noise content or unwanted DC content coming in the source signal will directly enter into the amplifier and may gets amplified. That is what the problem we have noticed in the previous coupling scheme. But here, due to the presence of this capacitor, whenever the input signal is arriving with certain amount of unwanted DC component or noise content, this capacitor will stop it or block it at the input side itself, so that noise will not even get permission to enter into the amplifier. Therefore, noise amplification is avoided. This is the other advantage of this coupling scheme. Then, of course, this coupling scheme also suffers few drawbacks. Let us consider them one by one. First one, DC signal amplification is not possible. Understandable? When the moment you place this capacitor here, you are indirectly accepting that you don't want any DC signal to enter into the amplifier. Why? Because capacitor, this coupling capacitor will block the DC components at the input side itself. So, DC signal amplification is not possible. That is the first drawback of the circuit. Then second one is signals at very low frequencies can't be amplified. Of course, for this, if you again go back to the previous slide, look into this, just look into this frequency response. Here itself you can easily understand that signals in this low frequency range cannot be amplified. Signals from FL onwards only signal can be amplified. So, signals at very low frequencies cannot be amplified is the next disadvantage of the circuit. Then coming to the third drawback of this circuit, improper impedance matching. Here also there is no flexibility for us to adjust the output resistance of the last stage which is going to interact with the load. You cannot maintain impedance matching between output stage and the load. That is the another drawback of this coupling scheme. Now let us go for transformer coupling scheme. Again, of course, if you look into this coupling scheme, the input signal is applied to the first stage and the output of first stage is coupled to the second input of second stage via a transformer. Then the output of second stage is coupled to the load via a transformer. Hence, we can claim that this is a transformer coupling scheme. Now, let us consider the merits and demerits of this coupling scheme one by one. First one, excellent impedance matching. Of course, understandable. We know when the load is connected here, when the load is about to be connected here, if you just look at that load which is connected to the output section or the output transformer of this circuit, here the impedance of this load is to be made very similar, or the output impedance of this amplifier is to be made compatible with the load resistance, then only impedance matching is possible. That one can be easily achieved with proper selection of the number of turns in the primary and the number of turns in the secondary of the transformer. As a result, impedance matching is easily possible. Why? Because the output resistance of the second stage can be adjusted with respect to the load resistance connected in the circuit, with respect to the load connected in the circuit. As a result, impedance matching can be easily achieved in this particular coupling scheme. That is the biggest advantage of this circuit. Then second one, signals at specific narrow range of frequencies can be amplified with high gain. Of course, this one you can understand just by looking at the frequency response of this transformer coupling schemes. If you look at the frequency response of a transformer coupled amplifiers, the frequency response will be generally more or less will be like this, where if you carefully observe, signals in a specific range of frequencies between FL and FH can be amplified. in a very narrow range of frequencies, signals can be amplified with high amount of gain. Gain will be very high in the amplifiers. As a result, signals at a specific narrow range of frequencies can be amplified with high gain. That is the second advantage of this coupling scheme. Third one, power consumption is very less in the amplifier. Of course, when you are using transformers as load at the load section, when from the power supply, when the DC current is passing through this transistor, this primary winding of transformer will act as short circuit, ideally short circuit otherwise, and therefore the amount of DC wastage or DC power wastage at the primary winding of the transformer will be 0 ideally. Similarly, even if you look at the second stage, whenever DC current is passing through this primary winding, the amount of DC power wastage at the transformer primary winding will be 0 ideally. That means what I am trying to convey to you is, because of the transformers used at the load section, the power wastage at the load section is considerably minimized, largely minimized. As a result of that, the power wastage in transformer coupled amplifiers will be very less when compared with conventional RC coupled amplifiers. When you have a resistive load at the collector in conventional RC coupled amplifiers, huge amount of more than 50% of power gets wasted at the collector, resistive collector load in conventional RC coupled amplifiers, where due to the usage of transformers at the load section in transformer coupled amplifiers, the power wastage at the load section is highly minimized. That is the another biggest advantage of this circuit. Now let us look into the disadvantages of this. Of course, understandable, the moment you connect transformers, in the moment you start or you have decided to use transformers in your amplifier circuit, you have to be get ready for the noise made by the transformers. We know transformers technically, of course technically people say the noise made by transformer is humming. The humming of transformer may be delivered into the output in the form of noise into the output of the amplifier. That is the fundamental drawback of the circuit. Of course, the transformers used as coupling elements are large in size and costly also. These are the two serious drawbacks of transformer coupling. Finally, let us look into tuned circuit or inductive coupling. If you look at the circuit diagram here, example circuit I have shown here, the output of first stage is coupled to the second stage via an inductor or LC tuned circuit. The output of second stage is coupled to the input of third stage via LC tuned circuit or tank circuit, and the output of third stage is coupled to the load via an LC tuned circuit or tank circuit, and so on. That is why this type of coupling scheme is popularly called as tuned circuit coupling or inductive coupling. Now let us look into the advantage and disadvantage of this coupling scheme. If you look into the first advantage, signals at a specific narrow range of frequencies can be amplified to maximum extent. Of course, this can be understood by considering the frequency response of this tuned circuit coupled amplifiers or tuned amplifiers otherwise. This is the rough frequency response of tuned circuit coupled based amplifiers or simply tuned amplifiers, where gain will be maximum at a frequency called F0, operating frequency or resonant frequency, and signals at that frequency only gets amplified, or signals just above and below to that particular frequency gets amplified. Means signals in very narrow range of frequencies only gets amplified in tuned circuit based multi-stage amplifiers, tuned circuit coupled multi-stage amplifiers. As a result, only desired signals can be amplified to high extent and unwanted signals are completely rejected. That is the biggest advantage of this type of coupling scheme. And the second advantage is proper isolation of DC conditions among the individual amplifier stages. Of course, because of the capacitor present between first stage and second stage and third stage and so on, there is a proper isolation of DC conditions among individual stages. As a result, operating point of individual stages will be stable. As a result, faithful amplification is guaranteed in this type of coupling schemes also. These are the advantages of this coupling scheme. Now, let us look into the disadvantages. Of course, if you look at the frequency response, just I have shown just now to you, bandwidth is very narrow. Of course, I have mentioned that as an advantage. If you want to look into that also as a disadvantage, bandwidth is very narrow. Whenever we want some wide range of frequencies to be amplified, not possible in this particular case. Then, inductor used as coupling element is large in size and not compatible for IC design. Of course, if you want to implement this circuit in integrated circuits, inductors are not suited or they are not compatible for IC design. This is another drawback in this case. These are the drawbacks of this particular couplings. With this, I conclude the merits and demerits of various coupling schemes. Let me summarize. While constructing a multi-stage amplifier, we have to use a coupling element, maybe a single connecting wire or a capacitor or a transformer or an inductor we are supposed to use as a coupling element. Based on that, there are 4 coupling schemes available. One is direct coupling scheme, second one RC or capacitive coupling, third one transformer coupling, and fourth one inductive coupling. We have discussed about the merits and demerits of all these 4 coupling schemes in detail. In the next class, we will see how to design a multi-stage amplifier and the analysis of a multi-stage amplifier in our next video lecture. Thank you.